Have you ever stopped to think about why your coffee goes cold but your iced tea never just heats itself up? Or how a giant, sprawling power plant and a little ice cube melting on your counter are actually following the exact same set of rules? Well, that, my friends, is thermodynamics. It sounds like a big, scary word from a physics textbook, I know, but it's really the science of energy that's running the whole show.
It's a weird question, right? I mean, on the one hand, you have something you see every single day. On the other, you've got this massive piece of human engineering. They seem worlds apart, and yet, deep down, they're both playing the same game by the same rulebook.
And here it is, the big reveal. They're both governed by what we call the thermal sciences. You can think of it as a team of three. You've got heat transfer, which is all about how heat gets from one place to another. You have fluid mechanics, which covers how liquids and gases move around. And then, right there at the heart of it all, the big boss is thermodynamics, the science of energy itself.
So, to really get a grip on this, let's start with the big picture. Let's dive into section 1 and ask the most basic question. What is energy, and what are the fundamental rules of the game?
Okay, so here's the official definition. Thermodynamics is the study of energy, how it changes form, and how it interacts with matter. But what does that really mean? Well, the whole entire field is built on two incredibly simple but powerful laws. You can't make mass out of thin air, and you can't destroy it. Same for energy. All you can do is change it from one form to another. You know, like turning the chemical energy in gasoline into the energy of your car moving down the road.
All right, so if thermodynamics is the game, the first thing we have to do is define the playing field. That's what section 2 is all about. How we draw a little box around the piece of the universe we want to study.
In any thermal problem, you gotta pick your main character. We call it the system. It's just whatever we decide to focus on. Could be a single engine, one tiny molecule, or heck, the entire planet. And everything else, the entire rest of the universe, we just lump all of that together and call it the surroundings. Simple enough, right?
Now, these systems basically come in two main flavors. First up, you have a closed system. Think of a sealed can of soup. The amount of soup in there is fixed. No mass gets in or out. Sure, you can heat it up, so energy can cross the boundary, but the actual stuff is trapped. On the other hand, you have an open system. That's more like a river. Water is constantly flowing in and flowing out. Both mass and energy can cross the boundary.
And this shows the difference perfectly. Over on the left, you see gas trapped inside a piston. That gas isn't going anywhere, right? The amount is fixed. That's a classic closed system. But on the right, you've got an engine core. You have air and fuel constantly rushing in and exhaust constantly rushing out. It's a classic open system. And figuring out which one you're dealing with is always step one.
Okay, so we've picked our system. Now what? Well, we need a way to describe it. We need a way to take a snapshot of its condition at any given moment. So that brings us to section 3, describing a system's state.
We do this using properties, and just like systems, they come in two flavors. You've got intensive properties, which don't care about how big the system is. Think about temperature or pressure. Then there are extensive properties, like mass or volume, that absolutely depend on the size. The easiest way to remember this is the cut-it-in-half test. If you take a room full of air and magically split it in half, the temperature in each half is the same, right? So temperature is intensive. But the volume of each half is now smaller, so volume is extensive.
Now this right here is a rule that is an absolute lifesaver for engineers. It's called the state postulate. And it basically says, look, for most systems, you don't need to know a million different things about it. All you need are two independent intensive properties, like temperature and pressure. If you know those two, you can figure out everything else you need to know. It's just like needing latitude and longitude to pinpoint any location on a map.
All right, so we've got the rules, we know the lingo, let's actually put this stuff to work. In section 4, we're going to follow the journey of a substance as it goes from a solid to a liquid to a gas, and we'll get to see all these ideas in action.
This thing here, it's called a phase diagram. Think of it like a treasure map for a substance like water. It tells you exactly what state it's going to be in, solid, liquid, or gas, based on its pressure and temperature. And check out this crazy spot right in the middle, the triple point. That's the one magical combination of pressure and temperature where you can have solid, liquid, and gas all hanging out together in perfect harmony. How cool is that?
So let's walk through that journey. Imagine we have a block of ice and we start heating it up, but we keep the pressure the same. At state 1, it's just a solid block of ice. As we add heat, we get to state 2, and it starts to melt into a slushy mess of ice and water. Add more heat, and boom, at state 3, it's all liquid water. Keep pouring on the heat, and it starts to boil. That's state 4, a bubbling mix of liquid and steam. And finally, once that last drop of water turns to steam, we hit state 5, superheated vapor.
So this chart, this TV diagram, lets us see that whole journey we just talked about on a map. We start way over on the left as a liquid. As we add heat, we move to the right until we hit the edge of that big hill in the middle. Engineers call that the vapor dome. Everything happening inside that dome is the boiling process, that mix of liquid and vapor. And once we come out the other side, we're in the superheated vapor zone. This map tells us exactly what's happening every step of the way.
Okay, these diagrams are awesome, right? They give you a real feel, a real intuition for what's happening. But you can't build a rocket engine with a feeling. For real-world engineering, you need precision. And that means it's time for our final section, moving from diagrams to equations.
Yeah, exactly. Because just pointing at a chart isn't going to cut it when you're trying to design a power plant or a jet engine. For that kind of work, you need the cold, hard precision of math. This is where we take those beautiful curves and those intuitive diagrams and translate them into powerful equations.
And if you've ever taken a science class, you've probably run into this guy before. It's arguably the most famous equation in all of thermodynamics, the ideal gas law, PV equals RT. It looks so simple, right? But this elegant little formula is an absolute powerhouse. It perfectly connects the pressure, volume, and temperature of a gas. And for a huge number of real-world jobs, from designing car engines to predicting the weather, it's an engineer's best friend.
So look how far we've come. We started by asking what a melting ice cube and a nuclear power plant have in common, and we've ended up with the actual equations that power modern engineering. See, thermodynamics isn't just theory. It's the fundamental rulebook for energy. And so that leaves us with a really big question. Now that we know the rules of the game, how can we use them to engineer a smarter, more efficient, and more sustainable world?